Hello, and welcome to Lecture 7 of AMAT502 at UAlbany. Today we're going to be talking about some topics which are a little on the theoretical end, but it's important to know just so you have some better cultural context of computer science as you move forward in your data science studies. Specifically, we're going to be focusing on subjects which you might call one-liners. One-liners are essentially very efficient ways of writing programs that all live on a single line. One of the best examples of this, which we will be using frequently in this class, is that of list comprehension. Along with list comprehension, it's good to know a little bit about lambda functions, which are essentially ways of defining functions without actually naming them. And then finally, we're going to conclude today with a quick introduction to object-oriented programming, which we're going to pursue in the next lecture. All right, without further ado, let's get started. So again, there's going to be two main parts. First part is going to be tricks with lists and lambda functions. We're going to do a quick recap of how we can do fancy list or string extraction using the colon operator. We're going to think of list comprehension as a tool which creates a new list based on another list in a nice single readable line. Finally, we'll talk about lambda functions and get to some of my favorite subjects, which is related to the contents of this wonderful book, SICP, Structure and Interpretation of Computer Programs. Then we're going to conclude with a quick introduction to object-oriented programming, talk about attributes and methods, and focusing on the first two topics of object-oriented programming, which are the functions init and self. All right, so as a quick recap, remember that if ever I have a list or string or any sort of iterable object, I can extract the sub-iterable substring or sublist using XABS, where A indicates the start index, B indicates the stop index +1, and S indicates the step size. Here are some other tricks which we've already seen. If we have X square brackets colon with no further arguments, it inserts default values with 0 as the default start and length of X as the default stop. Additionally, we can feed an argument before the colon and nothing after, which specifies the start index. Try to remember what happens if you just provide a second argument, meaning X blank colon B. All right, once you've thought about that, we'll continue. All right, so here are two more tricks. One is using the first two as default arguments, but specifying the step size. And one thing which I didn't tell you, given that we are really focusing on trying to use recursion to reverse strings, is you can always do a nice way of reversing something by specifying -1 or -2. -1 will reverse, -2 will skip every other step and reverse. All right, let's do some examples. So one of my favorite openings, stately plump Buck Mulligan came from the stairhead bearing a bowl of lather on which a mirror and a razor lay crossed. I hope you recognize the opening line of James Joyce's Ulysses. Let's see what happens when I execute each of these commands. Very good. Stately plump Buck Mulligan. Those are the first 30 characters of that string. Additionally, I could assume the first two entries are default values, start and stop, and then take every other character. You'll get say I'm mokomukayafo. It actually reads closer to Finnegan's Wake. Alternatively, we have a slick way of built-in indexing, which allows us to reverse a string in Python without needing to write a function. And that's just by using : -1. And here again, we get to have stately plump Buck Mulligan came from the stairhead bearing a bowl of lather on which a laser and a mirror, on which a mirror and another razor blade crossed, all listed backwards. List comprehension is a tool that allows us to replace loops that creates new lists from old lists with a single line of code. So we've already been familiar with some of the slicing and syntax there, but now we're going to use some more fancy notation inscribed inside of square brackets. So for example, if I want to assign a value to the letter L, which happens to be a list, one way I can populate this list is using an expression, something that's written in Python, along with the reserved word for, along with some other variable name, we call that item, and wherever that variable lies inside of another list. So let's go ahead and see how we can use this nice one-line program to do some common tasks. So for example, imagine I initialize a string H with the word human. So if I asked, let me go ahead and make a list using the characters in the string human, one thing I could do is initialize my list letters to be an empty list, and then declare that for I in H, where H is my string human, I'm going to append each letter one entry at a time. And of course, in order to view the output, I'll use print. So quick question. Why did we use print instead of return? Once you've thought about that for a little bit, you can see that we're not defining this as a function, and return always needs to be inside a function body. All right, well now let's see how we accomplish this task entirely in a single line using list comprehension. So we've already initialized, we've already declared what our string H is, it's human. And now I'm going to use the syntax L, where I populate the entries of L with I for I in my other list H. And let's see what happens when I execute this. I get exactly the same output. So I was able to condense essentially these three lines into a single line by using list comprehension. List comprehension is going to be hugely useful as we move on to using more array-based arguments and as we do more scientific computing. There's another option you should be aware of, which is that you can do list comprehension, but also have conditionals. This allows us to selectively include entries in our list by applying another conditional. The way we apply a conditional is we take exactly the expression that we already used in list comprehension, where we have an expression for some I or item in our list, and then we go ahead and include in our square brackets if some conditional is true, where conditional, currently written in italics, is evaluated as some Boolean. Okay, so here I'm going to show you two ways in which we can go store a list with the entries x squared for x lying in the range from 2 to 15, where we only include those entries that are divisible by 3. I just spoke that program aloud, and indeed Python's flexible enough that you can write that in a single line surrounded by square brackets, and it'll know what to do. So again, just to compare, we get the same output, but in this version where we don't use list comprehension, we end up having to initialize our list, and then we write a for loop, just as we do here, for x in range. Here we call it for I in range. And then instead of using colon, indenting, and then applying a conditional, and only when that conditional is satisfied do we actually append, I was able to do that all using list comprehension and just by appending that if statement. If x divided by 3 equals 0, which means x is divisible by 3. All right, so hopefully by now you can see some of the power of list comprehension. We'll do plenty of exercises to emphasize this and drill this concept in. For example, consider the following finger exercise. And I encourage you to just be exploratory with the sort of flexible syntax of Python. Just try doing things and see what happens. So in this exercise, you're asked to make a single list that has as entries all possible sums of the elements in the list 3, 5, 6, and 10, 13, 27. What I mean by this is we want to return a list of length 9, where first we consider 3 plus 10, 3 plus 13, 3 plus 27, which gives us 13, 16, and 30. And then it moves on to the next entry in our list and considers 5 plus 10, 5 plus 13, 5 plus 27, which gives us 15, 18, 32. And then moves on to our third and final element of our first list, 6, and then adds 6 plus 10, 6 plus 13, and 6 plus 27, which gives us the last 3 entries of our list. So go ahead and see if you can do that in a single line using list comprehension. Okay, we'll go over that solution in class. Now we're on to one of my favorite topics, one which we're not going to get into much depth with, but I want you all to be aware of it, and we'll start to take a peek at what lambda functions can do, and some of the features of dealing with languages like Python, where you can argue with objects in a way which you might not normally find intuitive. So this picture right here is selected from the cover of the second edition of Structure and Interpretation of Computer Programs by Harold Abelson, Gerald J. Sussman, and Julie Sussman. A composite photo of which is shown here on the back. This was the book I used when I learned computer science, when I was an undergrad, for the course 6001, where we used a language called Scheme. Scheme is a variant of Lisp, which heavily uses, although it's not completely dependent on, notion of lambda calculus, which is where the term lambda functions gets its name. You'll notice lambda is this Greek letter that appears right here. I encourage you to stare at this picture and look at it. All right, so getting on with the main content. Lambda functions are sometimes called anonymous functions. These are functions that have no name. Remember that when we normally define a function, we use the keyword def to define a function, where the next thing we have to supply is a name for our function. In this case, I called it my function. We then follow that string, which is the name of our function, my function, with round brackets and a list of parameters, which we are going to be supplied and used in the function. Then by using a colon and indenting, we have our function body. And after doing some computation, we want to return something. Notice that we have to give the function a name, which in this case is my function. But we can also circumvent this by using lambda, which Python highlights in green as it knows it is a reserved word, sometimes called a keyword. This is how we're going to define anonymous functions. So the syntax for lambda is I provide some arguments, separate with a colon, and then also have some expression. Again, all in one line. So unlike in the definition of my function, where we had to indent on a new line the content of the function body, here we can do everything on a single line. So notice a couple things. We have defined a function without actually naming it. And one thing that you need to note with lambda functions is that you can supply as many arguments as you like from 0 to n, but you can only have one expression using them. All right, let's see this in action. All right, so here we have h. H is a variable, which we're going to assign the expression lambda xyz colon x times y times z. And notice that in this next line, I use the variable h, but I surround it by round brackets and I supply some numbers. This is unusual. We haven't normally seen how we can take a variable name and then just go ahead and append round brackets to then call some values for that function. But let's make sure it works. Indeed it does. It takes 2 times 3 times 5, which is 6 times 5, which is 30. All right, so h has now been defined in a single line without using the keyword def, and instead using the keyword lambda, followed by its arguments, not using round brackets, and then a single expression using those arguments. And then I was able to call this function and supply those formal parameters that were then bound to these variables, x, y, and z. All right, let's do some more complicated examples. But before they do that, let me just try to point out, why do we care? So I've borrowed this image from David Beasley, who is the author of the book Python Essential Reference by Addison Wesley. If you're looking for a more comprehensive book, this might be one that you consider because it's very thorough and has lots of information and focuses on more of a developer's standpoint. You'll see there are essentially all the topics that we're covering in this class, along with some more detailed aspects of Python and some of the syntax. Anyways, David Beasley travels the country and runs workshops, and one of them was sort of teaching Python and SICP side by side. The reason why we like to look at Lambda functions and why I'm bringing such an emphasis on SICP is that it's a really good way of trying to understand foundational concepts in computer science. Indeed, one of the ways in which you can really understand concepts like variable binding, like when I write x equals 3, and things like substitution of a value into an expression, along with some of the other topics I've already alluded to in this class, such as function abstraction and application. I've alluded to the phrase, read a val print loop. All of this is sort of embodied in this notion of the lambda calculus. I'll also say that lambda functions, as they feature prominently in texts such as SICP, are really useful for understanding some of these key concepts. And I've linked to a couple of freely available copies of this textbook, one of which is in this PDF, which has been nicely included with certain images, which I encourage you to peruse. Or you can go to MIT Press's original website, which includes links to sample programming assignments. Again, I want to emphasize these are not in Python, but using a certain type of prefix notation language called scheme. Either way, the number one point, which I want you to remember or take away, is that lambda functions provide a way of returning functions in a way that respects abstraction. That's the key takeaway. Let's go ahead and see this in action. All right, so we all remember that in calculus, we have this important notion, which we think of as the derivative. The derivative is sometimes viewed as the slope of a tangent line to a curve, but it's actually a lot more than that. In fact, the derivative is an operator. It's an operator which is linear, and it can take in functions and return other functions. So let's see how we do that using Python. All right, so I'm going to define a function which I call derivative, and I'm going to supply it a function f. Notice I have no knowledge of the variables that go into define f. I'm just taking in f as a formal parameter. I'm not going to use the traditional non-limit definition of the derivative, which says what I do is I take my function, I step over some fixed amount, dx. I look at that function value of f of x plus dx. I then take the previous function value associated to x, and then I consider the slope of the secant line, which is given by the difference f of x plus dx minus f of x divided by my step size, which is dx, which I've gone ahead and just provided here as 0.001. So we take a small step size. All right, and then I'm going to define a candidate function. What's one of the first functions we want to be able to understand and how to differentiate? It's x squared. And of course, that's expressed in Python using x star star 2. All right, so I've returned whenever I have a value for x, f then returns the value x squared. All right, so now let's think about how derivative of f works. So The derivative of x squared, we all know, is 2x. That is itself a function. So I can pass it a value, let's say 0.5, and I'll get the slope of x squared at 0.5. Let's see what happens. All right, perfect. We've gotten what we expected, which is that derivative of x squared is 2x, which when we evaluate at x equals 0.5, gives us 2 times 0.5, which is 1. Of course, we have a little bit of error here because we're just using actually the slope of the secant line, not the actual true tangent line. All right. The reason we do that is we currently don't have a method of actually differentiating a function in Python. That's what we're going to use other special libraries for. All right, but let's go ahead and ask ourselves, what happens if I evaluate the type of derivative of f? So, it tells me what the output is. The output is an object, which is itself a function, which I can supply arguments to, which I did in the line above by then taking my object, which was returned from derivative of f, and then evaluating it on the value 0.5. Now think about what happened here. What really happened was that when we called derivative of f, we started to step through this function, which then returned a lambda expression, which then we needed to provide a value to, which was then bound to x. And then we computed f of x plus dx minus f of x divided by dx to the slope of the secant line at 0.5, which was the value we bound to x. Here's another example. So one of the greatest aspects of mathematics is once you want to substitute values into functions, have lots of arguments to deal with simpler functions. So here I give h a one-line definition using lambda. Lambda uses x, y, and z as my arguments, and then returns x times y times z. I can define g of z to just basically be h, where I've then bound 2 and 5 to the parameters x and y. And so this gives me a number when I evaluate it. But again, I could do what I did last time, which is ask for, what is the type of g? G is a function, which we know because we use the function argument. But notice that we didn't actually output a function. Rather, we took in an argument which provides a value. So that's why when I call g of z, g of 9, I get an integer because I'm multiplying a bunch of integers. This is to be contrasted with the output of derivative. The output of derivative was, even when I called it with its argument, f, returned a function. Whereas here, when I called g with its value, 9, returned an integer. All right. Let's consider another topic, which is going to be a useful shortcut when wanting to apply a function to a whole list of arguments without writing a for loop. It's another example of sort of doing something in one line. This is sometimes called the MapList function. And if you read one of the articles I linked to, you'll discover that I get some history about Lisp, which includes this statement about McCarthy, who wanted to, understand how to encode differentiation. And one of the innovators of Lisp, McCarthy, that's when he devised this MapList function. MapList is now implemented in almost every computer language, and Python's no exception. All right, so let's get down to actually how we use map. So as we've indicated, we're going to take a list of arguments and a function, and it's going to produce a list of outputs. Although that's not entirely true. We're going to have to wrap that and turn it into the type list. So in this example, I consider a list, which has entries 1, 14, 25, 4, 32, 114, and so on. And then I'm going to map function, which in this case is actually represented using a lambda expression, along with a list. All right, so what does this function do? Well, it takes in an argument x and returns x minus 200. So it's a pretty simple affine function. It has slope 1, and its y-intercept is now minus 200. The output of map is not actually going to be a list, which is why I then surround it in list with round brackets. So let's go ahead and see what happens. All right, it does exactly what you expect. Returns a list where it takes every entry in this list and subtracts 200 from it. That's just because that was what the function was. Took in an argument and subtracted 200 from it. All right. Let's do another example from calculus that will hopefully push your understanding of what's happening here. So I'm going to start with a list of powers. And I want to imagine creating a collection of functions of the form x to some power, where power is going to be indexed by this list of powers. All right. So powers equals 1, 2, 3, all as a list. And then I'm going to define a function, power of I, which takes in some parameter I, and then it returns the lambda expression that itself takes in an argument x and returns x to the I. So again, the output type of the function power of I is a function. All right, so let me go ahead and create a list, function list, which maps my function power of and my list of powers to another list of functions. And then for that list of functions, I'm going to apply my derivative operator, evaluated at 2, for items in my function list. So here I'm combining both lambda expressions and this comprehension. Sorry. Let's make sure everything works. Okay, this looks promising. If I just think about what the output of function list step is, it's going to create a list where I take the function power of and I supply it powers from this list, 1, 2, and 3. That's going to populate in the first entry the function x to the 1. And then in the next list entry, x squared. And then in the third list entry, x cubed. So I now have a list of functions. Of course, if I ask Python, what is the type of fun list? It'll tell me it's a list. But let's suppose I go ahead and access an entry in there, fun list 0. Tells me it's a function, which is exactly what we want. So this just also proves to you that lists are a very flexible data collection type, which allows you to store objects of multiple types in those lists, such as functions, which itself is an object type. All right. So fun list is a list of functions of the form x squared, x cubed. We know what the derivative of x is. It's just going to be 1. And notice it's 1 viewed as the constant function, meaning that if I supply the argument 2, it's still going to return 1. Now what about x squared? That's our second function in our list, fun list. It's going to return, so of course, x squared, but the derivative of x squared is 2x, just as we observed. And so 2x evaluated 2 is 4. And then finally, the last function in fun list is x cubed, whose derivative is 3x squared, which when we evaluate at 2 is 3 times 2 squared, which is 4, so times 3 gives us 12. And indeed, we get very close approximations of those values just by using this secant line definition of the derivative, which is something we can implement using primitive expressions of arithmetic already built into Python, with no need of using other functions or packages. So just to hammer home a point I alluded to earlier, map as a function will not return a list, but you need to wrap it and whatever collection type you want. This doesn't have to be a list. We've already considered examples of set and tuple. So let's go ahead and run through another example. So W equals range from -5 to 6. Let's go ahead and just ask, what is the type of W? It's a range type. A range type is a little more general than, is different than a list type or any other things. But the important thing is it's iterable. All right, so we already know that when we populate range from -5 to 6, it's going to start at -5 and end at one index before 6. That means +5. All right, so we've now got the integers from -5 to 5 inclusive. We then are going to map the function x squared and apply it to every entry in the list of W. When we do that, we then get exactly what we'd expect. The return values of x squared when applied to the entries in this list, namely 25, 16, 9, 4, and then up through symmetrically. That's because x squared is an even function, meaning it's symmetric about the y-axis. All right, so A and B, I both just stored using variables, but I was able to wrap those things using two of our data collection types, one being list. So list A returns a list, and set B returns a set. Now, remember, one of the features of set is it doesn't like having duplicate entries. So when I normally have this list, which illustrates the application of my function for the values between -5 and 5, set instead looks at the set of values returned by the function x squared when applied to the integers between -5 and 5. And that is a very important distinction, because if you just stared at the y-axis, meaning you took the graph x squared and projected onto the y-axis, you'd only get the set of values indicated here. So this shows you that even when you use the same map function, if you aggregate them into different data collection types, meaning a list or a set, you might get different outputs. Let's just ask ourselves, what happens when I ask for the type of A? It tells me it's a map type. So you are beginning to see there's this huge sort of zoology of object or data types in Python, which we've only just touched on. All right, so that concludes part 1 of this lecture. So the takeaway messages are, lambda expressions are useful for creating functions that we aren't necessarily going to use all the time, but if you want to be able to define them in one line or use them in the definition of other functions so that they are returning functions that can be then evaluated with later arguments, those might be instances where you want to use lambda expressions. Additionally, list comprehension is a very useful tool for condensing several lines of code into a single line. It's good to practice each of these so you look like you know what you're doing when you're using them. All right. We're now going to conclude our lecture today with a quick introduction to object-oriented programming. These are already some of the most fundamental concepts in computer science, lambda calculus and object-oriented programming. So it might be hubris to try to cover some of them in the same lecture, but we'll just start and do a little bit today. So object-oriented programming, sometimes called OOP, gives us a way to view objects as a thing that we want to operate on, which has attributes. Here is a nice graphic which sort of encapsulates, no pun intended, some of the operations which we can, or concepts that we encounter when studying object-oriented programming, such as class, methods, and attributes. And the rest of these we'll touch on later. Some of them we won't touch on at all. So it's best to learn using an example. So remember when we introduced dictionary types last lecture, we defined this dictionary associated to a car where we had keys that were entries such as make, model, color, and year. And then we bound values to these keys, like a Mazda 6, gray, and maybe a 2002 Mazda 6. We're going to go ahead and take that example and put it in its proper place by defining a whole class of objects where we want to emphasize these attributes, namely make, model, color, and year. Additionally, we want to know that there are some operations, specifically called methods, that we want to apply to our car object. Just arguing intuitively, you might think of start, park, and turn off as 3 methods or operations that you'd apply to a car or car-like object. All right, let's go ahead and start doing some code so you can see this in action. So the first statement that's going to be in our code is going to be something called a class, where we define a class. And I just want to go ahead and highlight some of the important aspects of a class. So we're going to define a car class. And one of the things we're going to need to do is have an initialize statement, which is going to essentially allow us to initialize our object along with its set of properties or descriptors, specifically called attributes. And then inside of this class function, we want to be able to define functions that then operate on our object in that sort of counterintuitive way, where we can take a variable, use that dot, and then apply the function after the variable name, instead of normally calling functions as we like to, where we have the function, and then in round brackets, we feed it the object. So just like in append, where we use a dot, object-oriented programming gives us a general framework for understanding that syntax. All right, let's get to it. So we don't even use the keyword def anymore. We now use the keyword class. So we're going to have a car class. And so this is a reserved word because it's highlighted in green. And then we're going to have the name of our class, which we call car. That becomes highlighted in blue. Just like when we define functions, they become highlighted in blue. All right. So the next step is we're going to define the specifics of our init function. Now this is a little weird because here we have to use 2 underscores. So it's underscore, underscore, init, underscore, underscore. And then we supply a whole collection of arguments. One of the key things you always need to have in this init function is this variable called self. You should think of self as a keyword, even though it's not highlighted in green, like class and def are. Following self, we then are going to supply some further arguments, which you want to think of as attributes associated to this object, which is of class car. Just as we alluded to earlier, we're going to use make, model, color, and year as some of our most important attributes when specifying an instance of a car object. As usual, we have our colon, and then each of the supplied arguments is then used to define new variables, which we put to the left. So self.make is going to be a new variable whose value is the supplied value make given to the init function. We then have self.model, which is going to be a new variable whose value is model, again, supplied by the function. And then similarly with color, and year. All right, so we've now defined class car, and we have populated our most important initial function, which is the init function for class car. So let's go ahead and call car, where we then supply the arguments Honda, Accord, Red, and 2013, which says that I'm going to create a car object that has these attributes. It's a Honda, it's an Accord specifically, has the color red, and its year is from 2013. So notice again, there's some weird things here. So car itself doesn't have any arguments that are supplied to it. That's what's handled by this init function. But when I go to call this, I don't use init when I'm calling the init function. Rather, I use the class name car. So that's right there. You'll also notice that the init function actually had 5 arguments: self, make, model, color, and year, but we only gave it 4. Now we have precedents for this. We already considered situations where certain functions can have default values. Here, things operate slightly differently. When I have my variable name to the left of the equal sign, my car, what happens under the hood is this actually gets bound to the value for self. So it's sort of secretly supplied as an argument. We'll summarize that in the next slide. But before doing that, I want to point out, how do we access these variables? Well, I just created a car. Assuming I stored this code, I'll do it again. And now I'm going to ask for what is the year and make of my car. And I'm going to access these variables by taking my car object and then penning the dot, and then the attribute that I'm interested in, year and make. And it prints here, because I'm asking it to print, the values 2013 and Honda. All right, so just to recap, there's 2 quasi keywords when defining classes. So the first is init, where I have 2 underscores on either side, and self. Every time we define a class, we want to have a function init that creates new variables associated to an instance or an object of this class. These new variables are called attributes. Notice that when we created the car object, my car, in our example, we did provide a make, model, color, and year, but we didn't supply a value for the variable self. That's where you want to kind of think of self as a default value. But the syntax is handled differently. Instead, when you actually defined your my car object by saying my car equals a car with these attributes, somehow Python knew to look at what variable name was used to the left and then bind that to the value self when it was calling class car. Additionally, you should notice that when we've been defining functions just inside of our code cells here, without using this class context, variables defined within the function were always called local, meaning their scope was limited to operations completely inside the function body. If I defined a variable inside a function and I tried calling it outside that function, it would say variable name undefined. But here, I'm able to actually access some of these inner attributes of the init function after I've created my instance of my car. This is where mycar.year is something that we can actually call outside of the function body, even though it looks like it's defined internal to init. All right, so one last topic for today. Methods. Methods we want to think of as functions that are defined internal to a class. In this case, the car class. So here are 2 examples of methods, which you want to think of maybe as operations, which you can perform on a car-like object. Namely, I can always start my car, and I want to be able to turn off my car. Again, I'm going to supply self as an argument to each of these methods. And the way that that's going to get bound or passed, again, is sort of different, where I'm going to have my variable name to the left, which gets bound to self, and then using my dot notation, and then whatever method I'm calling. So before I can really make sense of what these methods do, I should be careful to see what attributes are they operating on. I've expanded my list of attributes to include 2 more, namely a speed and whether or not it's on, which takes a Boolean value, either true or false. And whenever I initialize a car, I'm going to assume it's turned off to start. So self.on is going to be equal to false. Okay, let's go ahead and bring this into memory. All right, so I've now brought my car class into memory. And I've expanded my attributes beyond make, model, color, year to include speed and whether or not it's on. Start and turn off are 2 methods which allow me to toggle or mutate this attribute of whether or not my car is on or not. Okay, so let's run through this again. I create my car equals car, which is the name of my class. And then I've got Honda Accord Red 2013, just as before. Notice I didn't have to supply any more default values because my init function didn't ask for anything related to what the initial speed is, which I call self.speed, or whether or not it's on. These were all just sort of defined internal to the init function. Okay, so let's step through this. All right, so I've now created my car object called myCar. Let's suppose I ask for this attribute. Is it on? myCar.on returns false. That's because in this first line, all I did was initialize an instance of the car class called myCar, and it is always initialized to be off, which is expressed using the Boolean value false. All right, so let's suppose I try to call the start method. I want to start my car. So myCar.start. Notice again, I don't supply any arguments. That's because the only argument in the definition inside the class function, inside of class, had self as the only argument. All right, so when I run that, all that does is changes some attribute without actually returning anything. Well, let's suppose I go ahead and ask my little Python interpreter here to return the value associated to the variable myCar.on, which I want to think of as the attribute of whether or not my car is on. It's now true. So I've modified an internal characteristic of my object, my car, and that characteristic is saying that now my car is on. So you can think I put the key in the ignition and turned it on. All right, well, it's been a long day, so let's go ahead and turn it off. Again, it doesn't actually return anything. That's because this is a method that's being called, which is mutating some attribute of my object, my car. Just to make sure that that worked appropriately, let me check this attribute again. Great. My car is off because the on value is true, is false. All right, that's it for today. We'll pick up some of these concepts in object-oriented programming in our next lecture.